This conference will now be recorded.
Very good evening, students. Today we are back with the revision part of previous year JEE Advanced paper. Today we'll be discussing on modern physics part. So here we'll pick up questions from atoms, nuclei, dual nature of matter, and semiconductor physics. So let us start our discussion for today. So this question is from dual nature of matter. The work functions of silver and sodium are 4.6 and 2.3 electron volt respectively. The ratio of the slope of the stopping potential versus frequency plot for the silver to that of sodium is. That means you have to find out slope, like ratio of slope of silver to the slope of sodium. So this is the question. And what is the graph here? The stopping potential V versus frequency. So this you know very well that this question is from photoelectric effect, and we know photoelectric effect, the equation, the famous equation given by Einstein for photoelectric effect is written as this way, can be written as this way: maximum kinetic energy of the photoelectrons, K max, will be is equal to the energy of the incident photon and work function minus work function. So the excess energy of the photon, incident photon, will provide the kinetic energy to the photoelectrons. Okay, so this is the equation. So this equation, this kinetic energy is actually exactly equal to the stopping potential energy, EV. Okay, so I can write here EV is equal to h nu minus phi. Further, we can write V is equal to h by E nu minus phi. So look now, the stopping potential, better to write this as Vs, this stopping. So now see, from this particular equation, if we plot stopping potential Vs versus frequency of the incident, photon. Okay, then what is the slope? Slope will be given by, so slope will be given by h by E. You can see this. So slope will be given by h by E. So h by E is the slope. Okay, so here you can see E is the electronic charge and h is the Planck constant. As a whole, the slope is a constant. So the slope is a constant. It doesn't depend on, it does not depend on the value of the work function. It does not depend on the value of the work function. Therefore, the slope of any material, any metal, slope of stopping potential versus frequency of any metal will be the same for will be the same. So therefore, we can write this answer to be 1. Okay, slope for silver to the slope for sodium, these are actually equal, right? So this will be 1. So this is 1. Okay, so this is a problem from photoelectric effect, and it was from JEE Advanced 2013 paper. We'll go to the next page, next problem. So this is from nuclear physics or nuclei. A freshly prepared sample of radioisotope of half-life T half is given as 1386 seconds. Activity is given as 103. So activity is generally written as R is equal to N into lambda, and it is actually initial activity N0 lambda, we can say. Activity, this is given as 103, and ln2 is given as 0.693. The fraction of the initial number of nuclei, initial number of nuclei that decay in the first 80 seconds after the preparation of the sample. You have to find out the fraction of the initial number of nuclei that will decay in first 80 seconds after preparation of the sample. How do you do that? We know, so these are the informations given. Now look here, we can do it. See, the fraction will be obtained like this: 1 minus e to the power lambda into t. Okay, now see this factor, we can just, because this t is a second, 80 second, and lambda is given, lambda is not given anyway, so this term can be expanded up to first power, okay, or first uh, okay, so let us see. So this will be 1 minus lambda t, okay, and there will be further higher order terms of t will take up to first order term of t, then you get from here to be lambda into t, but lambda is not given, t is anyway given, t is here 80 seconds. And what is lambda? Lambda is obtained from t half, 0.693, like this. Okay, we'll put it here. So lambda is 0.693. Okay, t is 80 divided by, so this is actually t half also will be there in the denominator. T half is given as 1386. Okay, so this will be in percentage. Okay, now look, I can write this as 693 into 10 to the power minus 3 into 80 divided by 1386, and this is actually 2, and this will be 40. That means, you know, this will be 0.04, or if we write in percentage, okay, so this will initially it will not be percentage, so we can just express into percentage, so it will be nearly 4%. Okay, the fraction will be nearly 4%. So question was the fraction of the initial number of nuclei. So 4% of the initial number of nuclei will decay in first 80 seconds after the preparation of the sample. Okay, so this will be 4%. Now we'll move on to the next problem. This is again a good problem. We'll try to solve it. The kinetic energy of the alpha particle when nucleus of nucleus polonium at rest undergoes alpha decay is. So look here, this is polonium. It has atomic number 84 and mass number 210. Okay. So what is the question? You have to find out the kinetic energy. You have to find out the kinetic energy of the alpha particle in this decay. So kinetic energy of the alpha particle in this decay. Okay. So when the polonium is at rest, let us first just write the decay equation or decay relation. So that is He2He4. Okay, that means mass is 4 and 2 is the atomic number of alpha particle. So this is alpha particle, and then there will be the recoil or the daughter nuclei. Daughter nuclei will be lead. Okay, that will be lead. This will be 82 and this is 206. Okay, and at the same time there will be some energy released, that is actually Q value or Q. Okay, that is Q. So you know this Q value will be actually exactly equal to, but this Q value, how this Q value in reality comes out as the kinetic energy of alpha. Say this is kinetic energy of alpha and kinetic energy of the daughter nuclei. Okay, daughter nuclei, I will write Dn, daughter nuclei. So Q value will be actually manifested in the kinetic energy of the alpha particle and the kinetic energy of the daughter nuclei. Here it is Pb, actually I will write Pb. So that is the fundamental idea in this case. So first of all, let us find out what is Q value here. Q value will be, obviously you have to find out the masses of this atomic masses, original atomic masses of polonium. So polonium has got mass 209.98286, etc. We'll try to do in two ways. We'll just use these masses and see how different it is. Okay, this is the mass. So actually the Q value is nothing but the mass difference. Okay, mass defect into c square. So mass defect into c square. So this alpha particle has a mass of 4.002603 and this lead has mass 205.97455 into c square. So this is the mass defect into c square. That will give you the Q value. Okay, and this, if we just do the calculation, we see this is nearly 5.422 MeV. Let us do this 210 minus 4 minus 206. Actually this is not the actual way to do. That's why we need to actually know the actual masses of the masses of each element. So that's how you will get the mass defect, otherwise not. All right. So we have got the Q value. Now see, as I said, the Q value will be actually manifested in terms of kinetic energy of alpha particle and in terms of kinetic energy of the lead. K2 say this is lead. So this is another point to be noted. Now, from conservation of law of conservation of momentum. Momentum, what we can write? We can write the momentum. See, when this, so momentum will be conserved. That means, you know, if the alpha particle goes in this way with some momentum K1, linear momentum, or sorry, Pu1, say Pu1, then the recoil nucleus, or sorry, the daughter nucleus will recoil with the same momentum in the opposite direction, so that momentum conservation is satisfied. Okay, so that is what happens. Therefore, we can write from the conservation of momentum as 2 into K1 into mass of the alpha particle. This is square root, and square root of this is 2 into K2 into 206. Okay, that means this is 8K1. This is 2 into 206 K2. So from here we'll actually find out a relation between kinetic energy of the alpha particle and the daughter nuclei. So we have obtained a relation between, so we have obtained K1 is equal to 100 naught C by 2 into K2. This is one point. The other point is that K1 plus K2 is Q, right? Q means 5.44422, what we have already got. Now see, if I replace K2 from here, that means 2 K1 by 103. That is equal to 5.422. Now K1 into 105 divided by 103, 5.422. So now if I find out what is the status of this, or what is the value of kinetic energy of the first, sorry, alpha particle, from here we'll be able to get the kinetic energy of the alpha particle to be 5.319 MeV. So this is 5319 keV. So you can see there will be options like this. So the first option is the correct answer in this case. Okay. Now we'll move on to the next problem. This problem is also from photoelectric effect. So what is the question? Here the question is, that a metal surface is illuminated by light of two different wavelengths. So say lambda 1 is 248 nanometer and lambda 2 is 3 10 nanometer. So one metal surface is illuminated by two different wavelengths, lambda 1 and lambda 2. So this is what it is said. Okay, so separately, obviously separately they were illuminated, and the maximum speed of the photoelectron corresponding to the wavelength are u1 and u2. So the electron emits here, photoelectron emits here has kinetic speed u1, and due to this wavelength, photoelectron which is emitted has speed u2 over here. Okay, so this is the thing. Now u1 versus u2 is given as 2 by 1 or 2 itself. Okay, then what is the work function of the metal is nearly equal to. These are the options given. See, we can write down, or we can find out the energy corresponding to this wavelength. See, because these are the, okay, h nu, we know h nu, or hc by lambda, sorry, hc by lambda 1 is equal to, hc is given as this 1240 electron volt nanometer. I can directly put the nanometer over here, 248, right? So this will be nearly 5 electron volt, 5 electron volt ev, and hc by lambda 2, this will be similarly 1240 divided by 310 volts into nanometer. Ultimately energy will be actually in electron volt. Okay, if in nanometer, here nanometer will be there in the denominator, so nanometer will go off, or only electron volt will be there. So this is 4 electron volt. We have got the energies. Now see, we know Einstein's equation, photoelectric equation, hc by lambda 1 minus phi is equal to the half m u1 square, say. Similarly, hc by lambda 2 minus phi is equal to half m, this is electron only, both sides. Okay, so these are the two equations. Now let us see, if we take the ratio of these two. I'll just remove this. So we'll now take the ratio of these two equations. Equation number 1, equation number 2, we take ratio, then what we get, hc by lambda 1 minus phi divided by hc by lambda 2 minus phi is equal to u1 square divided by u2 square. Okay, now hc by lambda 1 is already, the value is 5 minus 5, and here it is 4 minus 5. Okay, and look here, u1 square by u2 square was given already. u1 by u2 was given as 2:1, so it will be 4 by 1. So I can just multiply. So 5 minus 5, this is 16, minus 4 5. Okay, so look, this will be 3 phi is equal to 11. Okay, 3 phi is equal to 11. So phi will be is equal to 11 by 3. So 3 3 2 3 6, again 6. So it is actually nearly 3.7 electron volt. Okay, nearly 3.7 electron volt. So this is the answer. Okay, I hope you have understood this. I am not repeating. Now we'll take up the last question for this session today. Look, this question is from atomic physics as well as the concept of photoelectric effect is required. So what is the question saying? The question saying, consider a hydrogen atom with its electron in the nth orbital. Electron is at the nth orbital, and electromagnetic radiation of wavelength 90 nanometer is used to ionize the atom. If the kinetic energy of the ejected electron is 10.4 electron volt, then the value of n. Then you have to find out what is the value of n. Okay. So consider a hydrogen atom with its electron in nth orbital. So when the electron is there in the nth orbital, so energy of the nth orbital I can write minus 13.6 by n square. This I will write. That means, so that means this is kind of okay. So this is the energy which is minimum you need to require, like you need to supply to the electron to ionize this. Okay, and electromagnetic radiation of wavelength 90 nanometer. So here also the incident photon is there, so I can find out the energy hc by lambda. See here hc is given as this is the nanometer, and here it is 90 nanometer I can write. Okay, so we'll have ultimately this by 90 electron volt energy. Okay, so we'll now see if the kinetic energy of the ejected electron is this. That means what? The electron, kinetic energy of the electron, see kinetic energy of the electron will be energy of the incident photon. First of all, incident photon, energy of incident photon minus energy of nth orbital, energy of nth orbital. Okay, so that will actually be this 10.4 electron volt. So EK is 10.4 electron volt is given. Incident radiation, we know this electron volt, and this is minus 13.6 by n square. So that's how it is. Now we have to do the simplification. Okay, so here if we divide 1242 by 90, we'll get something like 13.8 electron volt. This is the thing. So I have enough space here. So 10.4 EV is equal to 13.6 EV, sorry, 13.8 EV minus 13.6 by n square. So from here it will be easy to find out. So this is 10.4 minus, so let us do this simplification. This will be, this side will be 3.4 with the minus sign. Here it is 13.6 by m square. So m square will be 13.6 by 3.4. This is nothing but 4. So this implies n will be 2. Okay. So you had to find out actually what is the value of n here. The value of n you had to find out. So n is found to be 2. So this is how you have to solve the problems. We'll stop it here for today. We'll pick up many more questions from the modern physics part in the subsequent classes. So thank you for your patience. Bye for today.